Good evening and welcome to the 13th annual Carnegie Observatory Spring Lecture Series. My name is John Mulchaey. I'm the acting director at the observatories and the organizer of the series. And welcome to everybody. It's so great. I see we almost filled every seat this time. Before we start, I'd love to get a poll to find out how many of you have been here before to one of our lectures. That's most people, I would say. And who is this your first time you've been here? Oh, wow, that's a lot of people. Excellent. And for those of you, we like new people. It's great to have to spread the word. How many of the new people found out about us through social media? Some of you, yeah, excellent. We have a brand new social media campaign. We just started last month, so that's great. And the rest of you found out from some other means, probably newspapers or something. So welcome. It's great to have you here. I first want to mention our hosts for this event, A Noise Within, this great theater. I want to acknowledge their help in setting this series up and allowing us to be here. If you have never seen a play here, I highly recommend it. They have 3 plays, I think, going on right now. And so there's some brochures out in the front, so please take a look and come back and see one of their great theater productions. The other thing I want to thank is the Norris Foundation, which funds this lecture series and allows us to put it on every year. We have a really excellent series this year. It's starting with an awesome talk by me. But you should come to the other 3 just in case. They probably won't be as good, but you should. The next one is my boss after that, Matt Scott, who is actually the president of the Carnegie Institution for Science, the whole organization. The observatories is just one of 6 branches of Carnegie. And he's a biologist, so this will be our first non-astronomy talk, but we do hope you'll come back. He's a really fascinating speaker, and you'll learn a lot about biology. I know I will. And then the last 2 talks in our series this year are on 2 of the hottest topics that people are always asking us questions about. On April 27th, we have Juna Kohlmeier talking about black holes. And then on May 11th, we have a very special guest, who's Bob Kirshner from Harvard. There's some Kirshner fans.
He introduced us.
Oh, I see. You're not his kids, though, right? Okay. Yeah, his kids actually live in Los Angeles, so there was a chance that they were here. And Bob, I'll have to let him know this. And Bob will be here on May 11th talking about dark energy. He was one of the key players in that field. So 2 really exciting talks at the end. Let me see. I think that was all I was going to say. Can we get the lights dimmed a little bit? Because now we're going to start astronomy. Excellent. Beautiful. Beautiful. So tonight I want to show you a side of the universe you may have not seen before. And so I've titled my talk The Multiwavelength Universe. And I'll explain what that means in a little bit. But first, let me point out something that may not be obvious to everybody. And that's that astronomy is unlike almost every other science in the fact that if you're normally a scientist, you can create an experiment, you can go into a lab and run the experiment and hopefully get your answer back. In astronomy, we don't have that luxury. The universe is just way too big, and it's too far for us to ever actually go visit the places we would want to visit, right? So for astronomers, we have to rely on what the universe sends us. And what the universe sends us is light. And so everything we know pretty much about the universe comes from our ability to collect light. This is a beautiful image here of the Milky Way viewed over our Magellan Telescopes at Las Campanas Observatory. And it's through images at places like this where we actually try to piece together the story of the universe. And when we think of light, and astronomers, people always think of pictures like this one. This is Edwin Hubble, who was a famous Carnegie astronomer. Many of you will know from the Hubble Space Telescope, which is named after him. And here's Edwin Hubble looking through the 100-inch telescope up on Mount Wilson. First of all, we don't really look through telescopes anymore. People always think that, and I'm like, I haven't looked through a big telescope in many, many years. But the other thing is that astronomers like Hubble followed in the tradition that started 400 years earlier with Galileo, and that was looking at the universe with optical telescopes, or visible light. In other words, light our eyes can see. And so tonight I want to talk about the rest of the universe, because it turns out that the visible light that we see with our eyes is just a tiny fraction of the light that's emitted by the universe, and objects in the universe. And so in astronomy, we talk about what's known as the electromagnetic spectrum. This is the full range of light that exists. And this is a series of names that we've nicknamed various sorts of light, depending on their energy. And this is basically, this top line here is a sequence of light from the highest energies, which is gamma rays, and then X-rays, and then ultraviolet. You see visible light is this tiny little fraction there. That's all we see with our eye. And then there's the lower energy bands, which is infrared, microwave, and radio. And so if you really want to study the universe, tonight I'm going to try to convince you you really need to study objects across this entire range. Now, light behaves as a wave, and so there's a little diagram down here which just shows a wave. And astronomers like to talk about what we call wavelength. This is the distance between two peaks, the two peaks in a light wave. And this quantity wavelength is another way of describing the series. And you can see here, if you're in the gamma rays, you have things with very small wavelengths, all the way to the radio with things that are very big wavelengths. And so when I say a multi-wavelength view of the universe, what I mean is actually studying the universe over all these sorts of energy bands. So let's see. Now, you're actually familiar with all these sorts of bands of energy. You just may not know it. Visible light is, of course, what we see, and that's this little fragment right here. This diagram shows you many other applications of other sorts of light that we use every day in our lives. You're most familiar probably with things in the radio spectrum. We have, of course, AM and FM radio, TV, ultrasound. In the microwave band, we have things like your wireless phone and your wireless data, and of course, microwave ovens. So all of this stuff over here is stuff that you use every day, and it's just light. It's just light that's in the radio and microwave band passes. In the infrared, there's things like remote controls. The screening that you do at the airport is usually in the infrared. And of course, in the ultraviolet, you're all familiar with that. That's what gets you the sunburn and suntan, is the ultraviolet rays. X-rays we know about from medical work, dental X-rays, and your baggage at the airport actually gets screened with X-rays. So the one area that you may not be too familiar with is gamma rays. Gamma rays actually are used in some medical imaging techniques and also used for some cancer treatments. But because they're so powerful, we tend not to use them much. So the bottom line here is that there's actually a lot of sources of energy, other types of light. Even though you don't see them with your eye, you're using them every single day. So the other thing I like to point out here is that for us astronomers, it's often valuable to think of the electromagnetic spectrum as a range in temperature. That is the temperature of the objects. And so this is the same kind of plot I showed you before, starting with the gamma rays going through the radio, and where I've now labeled the temperatures. And so if you're thinking of something that emits a lot of gamma rays, it's in the billions of degrees. Something in the X-rays is in the millions of degrees. Most stars actually emit their light around 10,000 degrees. This includes the sun. The surface of the sun is about 6,000 degrees, and that corresponds to yellow light, which is, you can see right there. And that's why the sun looks yellow. It's just simply because it's peaking at that yellow wavelength. And then the cooler things like infrared, microwave, and radio waves really correspond to the colder regions of the universe. Now, you may ask the question, which is, why do we spend all of our time with visible telescopes if visible light is just a tiny fraction of the light emitted by the universe? And the answer is because it's the easiest. It's the easiest because it's the only portion, or one of the only two, actually radio being the other one, that actually reaches the ground. All other radiation from the universe is actually absorbed by the Earth's atmosphere. And this is really good, of course, because we would not like to be bombarded by X-rays and gamma rays and ultraviolet, and even some microwave and infrared radiation might not be great all the time. And so, thankfully, for us as human beings, our atmosphere absorbs most of the light. But it makes astronomy particularly tough. It means that, with the exception of optical research and radio, everything needs to be in space and above the Earth's atmosphere. And so it's for this reason that we've actually only had studies of other wavelengths really in the last 2 or 3 decades. And the real big accomplishment, losing my voice already, the real big breakthrough came with what's known as NASA's Great Observatories. These were 4 observatories that NASA built to study 4 wave bands in detail from space. And some of these you may be familiar with, some of them less so. There was the Compton Gamma Ray Observatory. It studied gamma rays. There's the Chandra X-ray Telescope. The one everybody will be familiar with is the Hubble Space Telescope. Of course, it produces these beautiful images, some of which I'll show you in a bit. What many people don't realize is that although Hubble looks invisible in optical light that you can see with your eye, it actually also covers a significant fraction of the ultraviolet and the infrared. So it actually does open up windows that we can't see from the ground. And then in the infrared, we had the Spitzer telescope. So these 4 telescopes, all launched within the last 25 years, really have revolutionized our understanding of the universe. Now, I want to quickly show you some examples of what objects you may be familiar with look like at different wave bands, and to show you why it's valuable to study them at different wave bands. So this is just 4 images of the sun. Here is the sun in the visible, this white, kind of boring-looking one. What you're seeing in a picture like this is actually what we call the surface of the sun. This is the part that's about 6,000 degrees. And it's remarkably uniform and boring. That's okay. That's why we love the sun. But if you look at other bands, like for instance the infrared, you start seeing these dark regions that show up. These are cold patches, cold dense regions on the surface of the sun. These correspond to what we know are sunspots. It's just a more dramatic view of sunspots. But if you go to the higher energies, like the ultraviolet and X-rays, you start seeing these little features here, like on the side here of the sun. These are really hot features. These are solar flares, mass being ejected from the sun. Most of the emission you see in the ultraviolet and X-ray is actually occurring above the surface of the sun, but it's only occurring kind of in spotty bits. And so only by studying the sun across all these wavelengths do you really get the complete picture of what the surface of the sun or near the surface of the sun is like. Okay, this is one of my favorite pictures here. This is 3 views of Saturn. This one will be very familiar to all of you. This is what you think Saturn looks like, because that's what Saturn would look like with your eye if you could look at it through the Hubble Space Telescope in this particular case. So it's a pretty spectacular view. But here on the middle and right are 2 other views in 2 different infrared bands, 2 different wavelengths of infrared light. And what you see is that in the infrared, Saturn looks quite different. In the visible image, what you're seeing here is actually just light from the sun being reflected off Saturn and off the rings. And it turns out Saturn's a pretty good reflector. That's why it looks like that. But when you get to the infrared, you'll see in this first band, a lot of the rings just disappear. And that's because the material that the rings are made of actually are absorbing the light from the sun at this wavelength. So the rings, and by the far infrared, by the time you get down here, the rings disappear entirely. Just all the sun's light at that particular wavelength is just absorbed by the little particles that make up the rings. The other thing that's quite interesting in this far band here is you start seeing this little feature up here. These are actually storms in Saturn. These are warm regions, and by warm, they're not really warm, but they're warm compared to the rest of Saturn. And they actually are emitting infrared emission. So Saturn does emit a little bit. But once again, only by looking at Saturn at these multi-wavelengths do you really get these different views. And here's a very famous Hubble Space Telescope image here on the left. This is what's known as the Pillars of Creation. It's a beautiful image. It actually doesn't even look real. When I first saw it, I thought this was fake. It's actually real. This is a Hubble Space Telescope in the visible. And then here's a new image that was taken very recently in the infrared, the same piece of the sky. And I hope you can see with your eye right away that they look very, very different. In the left panel here, what you have here is you have big pillars of dust. And in this dust, young stars are forming. This is the place where new stars are being created. And in fact, there's some new stars that have actually already kind of been created earlier. And these stars are, in fact, their radiation is blowing up this cloud. So this whole thing, this pillars of creation, is actually getting blown away and evaporated by these young stars. But if you look at the right of the infrared light is very good at seeing through dust. And so that's why it's good for your remote control. You can see through things. And so what you see here are all these stars all over the place that are just completely invisible in the visible. This is because the infrared light actually can get through the dust and clouds. And so you see this is an area where just a huge number of stars are being formed. Okay, and this is my last example before I get to the exciting stuff. This is the Whirlpool galaxy. It's a beautiful spiral galaxy many of you will be familiar with, in 5 different bands this time. And this is kind of what it looks like in the optical. This is what the Milky Way would look like if you could go outside of it and look down at it. And in the optical, you see stars like the sun, mostly yellowish stars. And you can see beautiful lanes of dust and such. If you move just a little bit over into the infrared, you actually are seeing different stars. These are just cool stars. And it turns out that in a galaxy like this, most of the stars are these cool red stars. Stars like the sun are actually fairly rare. And so that's what you see in the infrared. But even rarer than stars like the sun are extremely blue and young stars, and that's what you see in the ultraviolet here. These are the most massive stars we know about being formed. In the radio, what you're actually seeing is cold gas and dust. This is the stuff that new stars will be formed from. And in the X-ray, you're just seeing very hot regions where stars are being formed for the first time, especially there in the center. So once again, by looking at the galaxy in different ways, you really get a different view. Oops, I'm going to go back. Okay. So the question is, I've shown you some just examples that show you how looking at different wavelengths, you get a very different view. But how do we as astronomers use this data to answer questions? And so I thought that it would be kind of fun to go back over my career. I hit my 20-year anniversary recently. And I thought, let me look back at my career at how I've used multi-wavelength astronomy to answer interesting questions. I hope they're interesting. So I'm going to have 3 little stories for you. And the first one takes place now over 20 years ago, back in 1993 when I was a graduate student at the University of Maryland. And one day an astronomer named David Burstein came through. David Burstein was a really interesting guy. He was a guy who loved to look at pictures of galaxies. He just loved studying galaxies. And back in this time, this was before the internet, for our young astronomers in the crowd. We didn't have all these images we have with the Hubble Space Telescope of millions of galaxies, and we didn't have all the beautiful data we have. In fact, the best source of data we had was a survey from the 1950s, and this is called the Palomar Observatory Sky Survey. And this was a survey done actually at Palomar Observatory near San Diego by astronomers here in Pasadena at Caltech and Carnegie. What they did is they used the telescope and scanned the entire northern sky, taking images. And then these images were available to us astronomers on, and I was going to bring an example and I forgot, I apologize, on these beautiful pieces of, they were kind of like negatives, for those of you who remember old negatives. This very thin kind of see-through material with the images, the negatives, as you see here as an example. And we would put these negatives down on a light source, and you could actually, with an eyepiece, you then would go down and look at this thing and see what the galaxies look like in detail. This is how we did astronomy 20 years ago. It's changed quite dramatically. But anyhow, Dave Burstein had come through, and he had spent endless hours going through this plate with his eyepiece, looking at galaxies. And he said, I found this very peculiar galaxy. He said, it's NGC 2276. This is it right here. This is actually what the Palomar Sky Survey looked like, except you'd be looking at it in much more detail with your eye. And what he said is, when I first saw this galaxy, I thought it was a squish spider. He said he thought it was really on the plate. He actually thought that maybe in the process of when it somehow did look kind of like a squish spider. I think you can kind of see that now. And then he realized, oh no, this is actually a galaxy. And so this is a more modern view of the galaxy. And now, see, the young kids today are spoiled. They don't have to look at these old Palomar plates. This is really what the galaxy looks like in detail now. And you can see why he thought it was a squish spider, because it kind of has this round shape here, and then all the arms seem to be going on one side. And so the question he asked me, he goes, what could be causing this strange shape of this galaxy? Normally galaxies, as I showed you earlier, that whirlpool galaxy was very symmetric looking, and this is definitely not symmetric looking. Well, at the time I had been studying a phenomenon known as ram pressure stripping, and I told Dave, maybe this could be due to ram pressure stripping. So what is ram pressure stripping? I have a little movie, which I'll play for you to show you. Oh, hold on, now go back. I think I'm going to play, there it is. And so I don't know how visible it will be here. Ram pressure, here's the galaxy, and in this simulation, this is a theoretical simulation, the galaxy, it's actually an artist's rendition, but the galaxy is moving, and you'll see how the material is starting to stream behind it. And this is because the galaxy is moving very rapidly, in this case through a hidden hot gas cloud. So there would be a bunch of hot gas here, you just don't see it in the picture because it doesn't show visible light. But you see how the galaxy started getting these tails, kind of all in one direction. And so I told Dave, I said, well, that's kind of what seems to be happening in this NGC 2276. It has kind of this swept back look. You can imagine if it was kind of flying through hot gas, maybe it would have this swept back look. And so I said, why don't we write a proposal to see if we can find this hot gas that this galaxy might be moving through. And our idea was that there would be some little hot gas cloud up here, and that's what it was bumping into. At the time, there was a brand new X-ray telescope called ROSAT. It was a very small X-ray telescope, but it was what we had at the time. And so we decided we'll write a proposal and look for the hot gas that this squish spider galaxy might be bumping into. So let me first tell you a little bit about how actually this process goes, because it's very interesting, I think, for people who aren't astronomers. It's not so interesting for us astronomers, because it's a kind of a painful process. What happens in a case like this is you write a proposal saying, I want to observe NGC 2276 because I think it's bumping into this hot cloud that we can't see in the optical, but we might see in the X-ray. and then I need this much time to do that. So you write this proposal, and it goes off to ROSAT, and then ROSAT holds a committee of astronomers that then sit and review these proposals and decide which ones get time and which ones don't. And the reason it's a painful process is for something like the Hubble Space Telescope, for instance, 5 or 10% of the proposals that you write actually ever get time. So remember, all these proposals are being written by professional astronomers. HST, for instance, the Hubble, gets 1,000 proposals at once, and maybe every year, and maybe 70 or so of them will actually get time. Anyhow, so we wrote a proposal for ROSAT to look at this spider galaxy to see if it was in fact moving into an X-ray cloud. And they ranked the proposals at ROSAT at the time as A, B, and C. You might guess the A's were in fact the best proposals. That would be true. And the A's always got done. And if you were a B proposal, you might get done if you were lucky. And if you were a C proposal, they really hated your proposal. So needless to say, our proposal was ranked C. And they said, this is ridiculous. You're never going to see anything. And good luck. Pick something else to work on for your thesis, which is pretty much what I did. Anyhow, in the meantime, we got extremely, extremely lucky. Because what happens is when they go to schedule the telescope, they schedule all the A's, and then they try to fit in the B's that they can fit in. And there was a gap in the schedule, and they had nothing else to observe. So they decided to observe NGC 2276, even though the proposal had been ranked C. And so we ended up getting an observation for this, even though we really had no right to get it based on our proposal grade. That's the story, and that's the painful part. The good news is it actually ended up being a truly spectacular observation. And in fact, the next year when ROSAT was showing the team that evaluates the proposals, they went in and reminded everybody that they had given our proposal a C, and that maybe they should take a chance on more interesting things. So, that's a lesson learned. So that was good. Anyhow, this is what we saw, and it really is quite incredible. So this is 2276 again. This is another galaxy related to it, NGC 2300. And you see here in this purple-pink thing is a giant cloud of hot X-ray emitting gas. And it's really quite impressive. Just to put some numbers on it, it's first of all 10 million degrees. That's why it's emitted in the X-ray. But the distance across this thing is about 1 billion light years. This is not a small thing. All right, it's huge. And the thing is as I said earlier, I was expecting to see a little cloud up here, like tiny little thing, and that is not what this is, right? And so this was a big surprise. Oh, somebody? And this was really the first time we had seen a big X-ray cloud around around a small galaxy system. So a system like this with just 2 galaxies we refer to as a group of galaxies. There's actually a third one that's down here. These 3 galaxies are kind of traveling together in space. And this was the first time anybody had ever seen that these groups of galaxies are immersed in giant clouds of hot X-ray gas. We now know that there's a lot of systems like this, but this was really the first one. And the really remarkable thing is our own local group is in a system just like this. And so in fact, if you had X-ray eyes, you might actually be able to see that our own Milky Way is floating around in this hot gas as well. Okay, so this was really, really interesting, and not at what we expected. And then the question came about, well, why is this gas cloud here? Right? And we were not obviously expecting it because we didn't predict it. We predicted an X-ray cloud, just not this big one. And the other question is, when you have gas at 10 million degrees sitting in space in a cloud like this, it should disperse very quickly because the particles, when they're at 10 million degrees, are moving around so rapidly, the cloud will just disperse itself in space. So the question is, why does it exist at all? Which is why we weren't expecting it. And the answer is because something must be containing the cloud. Something is keeping it from escaping into space. And we believe that something is gravity. And there's a process we know about, and it happens in the sun, called hydrostatic equilibrium. And this is where 2 processes balance each other exactly and keep something maintained. In the sun, this is why the sun does not change shape. The sun, of course, has gravity, which is trying to contract it all the time. But there's gas pressure in the center by the nuclear fusion that actually is putting pressure outward. And so the sun is in an equilibrium state. And we believe the same exact thing is happening with this X-ray cloud in NGC 2276. It's an exact balance between gravity trying to push it in and gas pressure pushing it out. And it's to the point where the gas actually heats up to just the right temperature so that this balance happens. So this is really interesting because it says you can actually, if you can measure the temperature of the gas, which we've measured, you can actually go back and then calculate how much mass do I need to keep the cloud there. And so we did that, and that was a very surprising result as well. The result was that the mass required to keep the cloud there was actually much, much greater than the mass that we see in the two galaxies and in the purple gas if you add it up. In fact, it's less than 10% of the gas needed. And so this was one of the first times we were able to actually show that a system on this scale was actually dominated by what we call dark matter. That is, there must be about 90% of the system in some form of matter that is not emitting light or does not absorb light, but it has gravitational effects. And so this was really quite interesting. It's particularly interesting because systems like this, these small groups of galaxies, are actually the most dominant systems in the universe. Most galaxies, including our own, occur in these systems. So this meant if there was dark matter in this system, there's probably dark matter in all of them. And it meant there was a lot of dark matter, which we now know 20 years later, it seems pretty obvious, but at the time it was really not so obvious. I thought I would just show you a really interesting thing in case anybody heard this on the news. It was just over the weekend. We are still using X-ray 20 years later, X-ray observations and optical observations combined to study dark matter. And this is a beautiful new study done with ROSAT and HST. And this is actually much more complicated than the study I just described to you. And what this study did is they actually took systems like NGC 2300, but where there were two of them that had collided. And when you take two groups like this, or with these X-ray halos and dark matter, and collide them, what happens? Well, what happens is if you have two X-ray clouds, the X-ray clouds will end up smack together in the middle. But the galaxies actually, because galaxies are very few and far between, actually pass right through. And then so the question is, what happens to the dark matter? And that's what this study is dealing with. What this study did was it used a very interesting technique called gravitational lensing. What it's doing is it's looking at objects behind the cluster, and the mass of the cluster actually changes those objects on the sky. It distorts them. And based on that distortion, you can calculate the mass. And so what you can do is you can use this gravitational lensing to find the mass directly. And what this study shows you, let me see what's the best one to do. Some of these are more complicated than others. We'll do this one up here on the upper right-hand corner here. What you see in pink is actually the hot X-ray gas. And you see that in all these cases, the X-ray gas is kind of in the middle. That's because they pass through, and as I said, the gas kind of sticks together. But the blue actually shows where the mass is, where we think the dark matter actually is. And the interesting thing is the blue is always on the outside, you'll see. This is another really good one down here, or this one. And what this means is that when these two systems collided, the X-ray gas collided, the galaxies went right through, and the dark matter also went right through. And this is really important because what it tells us is that the dark matter did not go smack in the middle like the gas. It tells us that the dark matter apparently does not interact with itself. This is a really exciting result. It doesn't mean I know what the dark matter is, so don't ask me. What it means is that it can eliminate a lot of sorts of dark matter that we thought would actually be much more interacting with itself. Anyhow, so that's a recent result. Let me also just point out that last month, 2276 was back in the news 20 years after our first discovery for a quite different science result. This has to do with black holes. So for the last few decades, astronomers have known of two sorts of black holes. There are what we call small stellar black holes, and they're not that small, but they're, say, 5 to 30 times the size of the sun. And then we have what we know is called supermassive black holes. And these are black holes that are 1 million to 1 billion times the sun. And those occur in galaxies. And so the question has been for a long time, why is there nothing between 30 solar masses and 1 million? Because we think that these big supermassive black holes must have been built up in some way. So you think you would see something in between. And we haven't really seen them. Until last month, astronomers using the Chandra X-ray telescope I talked about earlier found this very close-up image of 2276. Now the pink is actually is X-ray data of the galaxy itself, very, very zoomed in. And they found this object here, and this is the radio picture of it. And based on the X-ray and radio properties, it appears to be a black hole. And it appears to be a black hole of 50,000 solar masses, which puts it right in the middle kind of these two ranges. And so we think that this is actually the first discovery of one of these intermediate mass black holes. So 2276 has probably led to two important discoveries, at least. So let me actually transition a little bit to black holes. That's the second thing I'm going to talk about. And as I just showed you a second ago, We know that X-ray emission is really good at seeing hot gas. I've just shown you an example of that in 2276. I also just showed you a second ago, though, that we used it for black holes. It turns out that the other thing besides hot gas is black holes that you use X-rays for. And X-rays are quite good because this material is swirling into black holes. It heats to millions of degrees and then emits a lot of X-rays. And so this is a really great photo. This on the right here, may not look terribly impressive compared to some of the things I'm going to show you. But this is the deepest image ever taken with the Hubble Space Telescope. It's just a tiny little chunk of it. And every one of the little blips you see here is a galaxy. And these are all very, very far away, some of them 10, 11 billion light years away. It's really quite impressive. This is actually the deepest X-ray image ever taken of the sky. It's of the same patch of sky. And everything you see here, every little blip you see here, is actually a supermassive black hole. It's a black hole that's accreting and emitting X-rays. And if you look carefully, it's really hard to tell, but all of these actually are in these galaxies. So there's a correlation, you just have to look very carefully. And so what we see here is you're seeing all these black holes accreting material and glowing in these normal galaxies. So it turns out that X-ray emission is a really great way, is a really great way to actually find black holes. So the second project I'm going to talk about was a project where I was looking for black holes. And I was working with a group from Harvard, and they were looking at deep Chandra images like the one I just showed you. And they found this very interesting source. And this is it here. It doesn't look terribly fantastic in X-ray emission. But the interesting thing about it is it's two sources, and they're both pretty bright, and they're very close to each other. And so when they saw this, they sent it to me and they said, what do you think? Is this possible that this is two black holes that are actually related to each other? And the reason we think that would be interesting is we think black holes must merge. Things do merge and combine in the universe all the time, but we've never caught one in action. And so this will look like a pretty good candidate for a merging black hole. The problem is that these two sources may be completely unrelated. It may be that one is very distant and one is nearby, and they're just projected on the sky. They could be two very nearby things that aren't black holes at all. You just can't tell entirely from the X-ray data alone. And the only way you can actually determine what they are is by going to the optical band and seeing what they seem to be associated with. And so I was asked, and I joined this team, and I said I would be happy to try to get some optical images of this system to figure out what it really is. So I began a long trip to Las Campanas Observatory, Chile. These are the telescopes we operate at Carnegie. And Las Campanas is down here. This is Santiago, which is the nearest big city. It's about 500 miles north or so. And I just wanted to give you guys kind of an idea of what it's like to be an astronomer. It sounds very glamorous. Sometimes it is glamorous. Sometimes it's not. This is a case where at least getting to Las Campanas is not terribly glamorous. And in fact, it's a very long trip. We usually fly from LA to Dallas. From Dallas to Santiago, that's 6,000 miles to put it in perspective. It's a pretty long, two long flights. When you get to Santiago, you then have to fly to a little town, a nice, lovely town called La Serena, Chile. That's another hour on the flight. And then you actually hop onto a bus and drive up the mountain about 3 hours. The whole process, from the time I leave my house to the time I get to the mountain, is a minimum of 24 hours. And often it's closer to 30. And I've done it 127 times. So, yeah, I'm very, it's insane. I've lived 10% of my life over the last 20 years in Chile. But there must be a reason. And the reason is because you get to this observatory and it's truly amazing, truly amazing. And this is just some pictures of the observatory. And you'll see, the first thing you'll notice is it's very brown. It's very brown because it's in the driest desert on the planet. And that's good for astronomy. We don't want rain. We don't want clouds. But you'll also notice that there's very little life. There's some green, not green stuff, I was going to say plants, but they're not green. They're actually brown. And then occasionally you see some really interesting things. This is a guanaco, which are these beautiful animals. And you're like, what is this guanaco doing at 8,000 feet on this mountain where there's nothing to eat? But somehow they're up there. So once you've spent all this time to get to the observatory, it's so far from anything that you actually really have to stay at the observatory. So somebody asked me this earlier today, so that's why I'm telling you this. We basically live at the observatory when I go. When I go, I'm there for a week, and I spend the whole week living at the observatory. I typically will start working at maybe 1 or 2 in the afternoon. I do calibrations and getting the telescope ready in the afternoon. I eat dinner. I go back, and then it's dark, and I observe all night long. I go to bed usually at 7 or 8 a.m., Me personally, I never sleep on the mountain, so I'm always up by noon, and then I'm back at work like 2 hours later. So it's really like a very long and very tiring process. But it is a beautiful place. And so what we do when we're there is we actually live in these little lodges. You can see them up here. And they have chefs and cooks for us, so it's not that bad. I'm making it sound worse than it really is. Once you get there, it's fine. It's just the getting there that's the hard part. And then it is a very tiring experience, but it's totally worth it. And it's worth it because of the spectacular telescopes and the spectacular conditions we have in Chile. There's really no question that Chile is the best site for astronomy in the world. It just has the most amazing, stable atmosphere and produces the best quality images. And this is the telescope that I was going to be using on this particular project. These are the Magellan telescopes. To put this in perspective, they're 6.5 meters. So the mirrors are about the size, I would say, of this stage, 21 feet. I mean, they're really quite incredible. These are the telescopes we get to use. This is the back side of one, so you can see here, this guy here is 6'4", and so it puts you in kind of perspective. That's the back side of the mirror. These are really, truly incredible telescopes. And this is me actually at the telescope. I should point out, that was the reason I put this photo in here. We actually don't look through the telescopes. I pointed that out earlier when we had that picture of Edwin Hubble looking through the telescope. To be fair, even Edwin Hubble didn't spend most of his time looking through telescopes. I'm sure that was a photo op. That picture. But he did at least look through them once in a while. Usually people took photographs through photographic plates. But in this case, we're not even in the dome anymore. They've actually moved us off from the telescope, and you sit in a room which we call the control room. And this is the control room for one of the Magellans. This is the Magellan 1 telescope. You see this guy over here. He's actually a Chilean who's operating the telescope. And all of these computer screens there are various diagnostics monitoring the conditions of the telescope. And that's what he does all night long. He makes sure the telescope is working for me. And then this is me sitting over here with my one little terminal, but I'm controlling the instrument. This is the camera that takes the pictures. I decide like what I'm going to point at, what I want to expose, how long. All of that is on me. So I finally, after 30 hours, have made it to Magellan. Now back to the story. But I wanted to give you that backstory. I think it's important for people to understand the process. This is back to our possible double X-ray, well, it's a double X-ray source. Is it two black holes? So when I took the image and it came off the telescopes on the screen, I knew instantaneously that it was a very exciting result. Because what we found was, in fact, those two X-ray sources are associated with two galaxies. This is one of them, the center of one, this is the other one. But what's particularly interesting about these galaxies, these don't look terribly spectacular because they're very far away, are these what we call tidal tails. So you see this feature here and this little one over here. This is a sure sign that these two galaxies are actually in the process of interacting. And what makes that interesting is because, as I said earlier, if that means that these two black holes are sitting in two galaxies that are actually interacting, this means the two black holes, in fact, are related to each other and are probably very close to merging very soon. And so this is the picture. This is now the X-ray emission on top of the optical emission. So you see the tails, and there the black holes line up right on the two galaxies, dead on. And so, in fact, once we measure the distance of these galaxies, they're about 5 billion light years away. They're pretty far. You can actually determine the amount of energy that these black holes are putting out. And what you find is that they're putting out huge amounts of energy, and they, in fact, qualify as what we call as a quasar. So, in fact, this was really the discovery of the first binary quasar, two quasars that are merging and about to form a single galaxy. So now, one of the great things we've added at Carnegie in the last less than 10 years is a theory group. This is a group of people who actually do theoretical calculations and simulations and try to reproduce our observations. And so I'm going to show you a simulation. When I showed this to one of our young guys, he was just like, I can simulate that. I know what exactly is happening. And he did this really beautiful simulation. He's going to show us how this binary quasar formed. So here's one galaxy sitting along going. Here comes the second one. And you see that first it passes, and you already see the tidal tails forming from the first passage. The second one goes off for a while. Up here in the corner, if you can see it, this is counting down in billion years. So now it's already been 1 billion years. So the galaxy goes on up, but it's going to come back down at about 2 billion years because it's gravity, so it'll come back and loop back down. So let's see, here it comes. And the second time, it actually is not going to get away. And there you go, boom. And this is actually the simulation. This is where we think our observation is. You can see the results look pretty similar. But the great thing about the simulation is, while my observation is stuck, the simulation can run forward. And so you can see what happened. In fact, I turned around and it already happened. This binary quasar is so close to actually merging into a single galaxy. And what happens in this process is the two black holes will merge and form even a bigger supermassive black hole. And so, in fact, and probably a single quasar. And in the end, you end up with a single galaxy that looks quite different than the ones we started out with. But this happens quite frequently. So now, not to scare you, but this is going to happen to our own Milky Way. In about 4 billion years, we're going to merge with the Andromeda Galaxy, and we will look pretty much like this. The remarkable thing is that when you merge stars between these two systems, there's so much empty space between the stars that stars don't collide. And in fact, the sun will still exist. The solar system will probably still exist. By then, the sun will be pretty evil to us, and we will have been warped into the sun, probably, eaten up as the sun becomes a red giant. But other than that, it would be quite lovely. If you could survive, this is what the sky would look like. I just found this. I thought it was hilarious that somebody actually did an artwork for this. This is the Milky Way, and here's Andromeda now colliding with the Milky Way galaxy. But this is going to happen in 4 billion years, and we see this as this example showed us. So that's a really exciting thing. Okay. My third topic I wanted to talk about, I wanted to switch and go from the high energies. I've talked a lot about X-ray astronomy because that's really what I do mostly, to go to the other complete end of the multi-wavelength spectrum, and that is to look at radio emission and tell you a very, very recent story. This has only happened over the last year, and some of you may have seen this in the news recently. And the story takes place, this one starts in Australia with this beautiful telescope. This is the Parkes Radio Telescope. It's about 2 or 3 hours from Sydney, Australia. And a couple years ago, a very exciting discovery was made with this telescope. Astronomers who are going back looking through old data taken with this telescope, at old radio data, found these extremely bizarre bursts of energy in the radio. And you can't see the scale here. This is in milliseconds. It's really tiny. And so these blips that you see here were bursts of radio emission that lasted a millisecond or two. So it's a tiny, tiny fraction of a second. And the question is, what is the nature of these bursts? The interesting thing, we really don't know anything else quite like that in astronomy. The interesting thing, or the troubling part, was that these were found in old data. So by the time these had been found, these events had happened 2 to 3 years earlier. And so it was really too long to go back and try to figure out what happened. And so there are many possible explanations for this. If you go through the literature now in the last 2 or 3 years, there's so many papers that it's really quite interesting to read some of the crazy theories people have come up with. But the first thing that people thought of was that this was just fake. It was just some problem with the telescope, some telescope artifact. And that actually has fortunately now been ruled out because it's been seen by other telescopes. And so particularly last year, the Arecibo telescope saw the same sort of thing. So that kind of eliminates that. The other thing that people thought is maybe it's something terrestrial, maybe it's something here on Earth that's going on. Now, because of the distribution of these, we now know of other cases across the sky. We are pretty convinced they're not related to any phenomenon here on Earth. So that leaves kind of two really obvious candidates. And these are supernova and gamma ray bursts. Because these are explosions of stars that occur very far away in general, but they occur very, very abruptly. They occur, and it's a burst of energy. And so it kind of makes sense that maybe these fast radio bursts are associated with these supernovas or these gamma ray bursts. The really incredible thing is based on the few number of events we have, we actually only know of 7 of them, but we can extrapolate in astronomy. We do this all the time. Based on the 7 and the little bit of data we have, it appears that these bursts occur about 10,000 times a day across the sky. The problem is they're very quick, and you have to be pointed at the right place at the right time to see them. And fortunately for us, last year we actually caught one live. And so that's what I want to talk a little bit about. On May 14th, 2014, that beautiful telescope I showed you, that Parkes Radio Telescope, actually caught a fast radio burst live for the first time. And this is it. There's the burst. Once again, just a fraction of, just a millisecond. But the fact that we caught it live meant we could actually try to point other telescopes at it right away. And so we did that. Within one day, we actually used the same Magellan telescopes I talked about earlier. And we actually observed the area of the sky where the burst appeared to come from. Now, I should point out that the radio telescopes don't have great imaging quality, and so we only know that the burst came over a portion of the sky that's actually almost the size of the full moon. In fact, it's pretty large. And so that's a big area on the sky. That means a lot of things could be happening there. So we observed it with Magellan, actually for quite a long time. And the interesting thing was we found nothing. Nothing. What I mean by nothing is there were, of course, lots of stars and things in the field, but nothing varied. So what happened is we had looked at old images of the same patch of the sky and new images, and nothing had changed. And because this is a bursty thing, we would expect naturally that the radio burst would be associated with an optical. Something would flare and the optical go up or down or something. Nothing was found. So is this surprising? And the answer is yes, it's actually really surprising. And the reason it's surprising is because, as I said before, we really expected this thing to be associated with a supernova or a gamma ray burst. And gamma ray bursts and supernovas actually leave signatures long after they happen. Even though it's a bursty kind of activity, it's an explosion, you actually can see them for a long time. And this is an example. This is M99, it's a nearby galaxy. And up here in this little corner you see there's nothing there. This is before the supernova happened. And then this little picture up here shows it after. And you see this little optical after, what we call an optical afterglow. These actually exist for weeks or months after the supernova. It's not as bright as the initial supernova, but it's easily detectable. So the fact that we didn't see anything when we followed up the fast radio bursts tells us that it appears to be quite unlike a supernova or a gamma ray burst. So that is kind of surprising. And in fact, this is the most complicated plot I will ever have to show you, and it's not terribly complicated. We had two measurements with Magellan. We did one here, which was one day after the event, and then we did one about a couple months later, and that would be here. And both of these were non-detections, but these are kind of the flux limits. So on this plot, as you go up, things get brighter. So that's the easiest way to explain this. So if you look at this, this is our limit from the first time. We know it had to be that or fainter. But if you look at the supernova, this is what a supernova would have, this sort of supernova would have looked like. It would have been much, much brighter. So we can already, the fact that we didn't see anything here, eliminate this sort of supernova from the first observation. But there's some other sorts of supernova that actually get brighter in time, this optical afterglow. And so these are two examples of what those things look like. They're actually pretty faint initially, and then they get brighter, and same with this one here. But we have a second observation, which is here, and you'll see that our second observation is actually below those types. So what this means is, in fact, between the two observations, you can rule out all three of these types of supernova explosions. And these are associated also with the gamma ray bursts. So what this means is that seeing nothing actually tells us that it's not something, and that not something is it's apparently not a common sort of supernova or gamma ray burst. And so I like to put here, this is sometimes seeing nothing is very interesting. This is something we don't appreciate. It's of course great when you see something exciting, but sometimes seeing nothing is interesting. And this is a case. So the problem is when you put out a press release and say, we found this burst in real time, and we saw nothing. And I was quoted as saying, and I did say this is one of the biggest mysteries in the universe. You're asking for trouble. And then I got it. And the UK tabloids picked up on this right away. We were on the front page. I was quite happy in both cases. And they claimed that this must be aliens. And it made it sound like I said they were aliens. In case if any of you read that, I did not say they were aliens. I cannot rule out aliens. But I suspect it's highly unlikely that it's aliens. If it was aliens, you would expect these things to happen again. I should have pointed out that none of these fast radio bursts appear to happen a second time. So we think it's something that happens once and that's it. If it was an alien, they sent a signal, most likely we would get another signal. So I think we can probably rule out aliens, but anyhow. So that was just a couple stories about how multi-wavelength astronomy has been possible. And so I hope you enjoyed at least hearing some details about how we actually do the astronomy. So what is the future of these sorts of studies? In some ways, it's kind of a sad period coming because we're going to have to say goodbye to many of our old friends that, for instance, I've used over my entire career. I talked about these 4 NASA great observatories. The Compton Gamma Ray Observatory has already been dead for a while. The Chandra X-ray telescope is operating and operating quite well, but it will eventually, its detectors will degrade. It probably has 5 to 8 years left, which is not too bad, but it's certainly not what we'd want. Hubble Space Telescope, I hate to tell people, I know we all love Hubble. It's having its 25th anniversary in about 2 weeks. It's been an amazing telescope. But it will, in fact, probably have an end of life in about 2018 or 2019, which is coming up really soon. And there's really nothing we can do about it. It's not repairable at this point. And its detectors will just not be usable beyond that. And the Spitzer infrared telescope actually has already lost a significant fraction of its capabilities. And likely, it's doing a few things now, but it likely will not be around more than a year or two itself. So in fact, this entire generation of telescopes that folks like myself have built their career on will pretty much all be gone in the next few years. So that's the sad part. The good part, of course, is that there are other telescopes coming. And so one of them, which you heard about last year if you were at our series, which many of you were, is the James Webb Telescope. This is sold as the follow-up to Hubble. But really, it's more of a follow-up to Spitzer because it's really mostly an infrared telescope. It does cover a tiny bit of the optical window, but very small. And so some of the very spectacular blue images we've seen with Hubble, I showed you, like the pillars of creation and all that, you won't really get with the James Webb Telescope. But the infrared is really very interesting because this is the band where things at very high redshift, the early universe, that all the light from those stars is actually redshifted into that band. And so this telescope will allow us to really study the early universe in ways we haven't before. I should point out that how big this telescope is. This is the same size as our Magellan Telescope, the one I showed you on the ground. And so putting that in orbit is just going to be really incredible. And it's coming in 2018. So the hope is that this telescope and Hubble will overlap for about a year and they could cross-check them and everything, but we'll see if Hubble makes it. In terms of radio telescopes, this is also the future is very bright. Many of you may know about, we already have a beautiful new telescope called ALMA, which is in northern Chile. This is an array of telescopes that's used combined to produce very high resolution images in the millimeter bandpass. And this is a great telescope for looking at gas and dust in the early universe. And so it's really going to allow us, once again, to kind of extend our studies to the very high redshifts. And then there's a very ambitious telescope being built called the Square Kilometer Array. It's a whole kilometer, as you can guess, of telescopes. This is going to be really, really impressive. This telescope is likely to be in the southern hemisphere. It has yet to be decided exactly where. Right now, both Australia and South Africa want to build it. You'll notice a trend here. A lot of astronomy is moving to the south. And this is good for us at Carnegie because our telescopes are in the south. And there's a reason, because people understand the southern sky is really quite interesting. Unfortunately, the prospects are a bit grim for those of us who are interested in ultraviolet and X-ray astronomy, because in fact, at the moment, we have nothing on our slate that's definite. In the optical ultraviolet, there's a new idea called At Last, and I think it's called At Last because they figure we'll be waiting a long time to actually get to it. I really think that's true. I think it has another name, but it does add up to that. And the thing about At Last is it looks exceptionally exciting, but it's only in the very early stages. There's no money, and there's no plan to do it. And so I would say that we would be, it would be a miracle if this thing appeared before 2030, if it appears at all. And in the X-ray band, unfortunately, the US has pretty much no plans right now to build an X-ray telescope to follow up Chandra, which is really quite a shame. The Europeans have a telescope called Athena, but it has yet to be approved either. But I think it's more likely they will build something than we will. And if this gets built, it'll likely be 2028 or later. So unfortunately, this means there's going to be a gap in our ability to study the universe at ultraviolet and X-ray wavelengths, which, as I showed you earlier, X-rays are really quite interesting. But lastly, I'll point out the positive is, of course, we do have big telescopes here on the ground, so the visible bandpass has a bright future. This is one of 3 big telescopes being built in the world, and this is the one that's going to be at Las Campanas Observatory. It's called the Giant Magellan Telescope. And this consists of 7 mirrors. Each mirror is 8.4 meters in diameter. So each one of those single mirrors is already bigger than our current biggest telescopes we have at Las Campanas. And combined, they create effectively a 25-meter telescope. This is a hugely incredible telescope. It's a really beautiful instrument. This is just some of the things it will do. One is it'll be the most sensitive telescope ever built. It'll be sensitive enough that you can see a candle on the moon. I love that. I think that's pretty great to show you just how sensitive it will be. And the other thing is it will have 10 times the resolution of the Hubble Space Telescope. And so if you had this telescope here in Los Angeles and you pointed it at Las Vegas, you'd be able to resolve structure on a dime. It's really incredible. And so this telescope is coming in 2021. This is just a little simulation that shows you kind of where we're at. Here it is at the peak of our Las Campanas Observatory. The other thing that's worth reminding people about, the telescope's maybe 20 stories high. It's pretty large. It's about the size of a football stadium. But unlike football stadiums, it actually has to move. And it has to move smoothly, and it has to point. And so it's really a huge engineering task to build a telescope of this size. Now, the final design of the telescope is still not set, but we've already started on the mirrors, as many of you heard our talk last year from Wendy Friedman. We actually already have 3 mirrors of the 7 are in production, and we're hoping to start the 4th one later this year. And so by 2021, we should be on the sky in some form. And there it is looking out. So you'll notice the background of Chile. This just shows you how dry and desolate the observatory is. But this telescope will really make sure that Carnegie astronomers like myself will have all the access we need in the optical. So what I will say is, based on what I just talked about, between James W. Webb and the radio telescopes and this telescope, we will have some coverage of the multi-wavelength universe. It just won't be quite as complete as many of us had hoped. So my final thought here is that astronomy has really come a long way since the images I showed you of Hubble. And a lot of the progress, I think people don't realize, is not just building bigger telescopes in the visible and optical band, but it's actually the ability to look at the universe across multi-wavelengths. And so I hope that I've convinced you tonight that combining data from these various wave bands actually really can help you learn new things. And undoubtedly, we're ready for many more surprises as we build this next generation of telescopes. Thank you. I need some water. Okay, we have time. Well, I'll take a few questions if you want, and then other people, if you have any, are happy to come up. Any questions? Sure.
Just out of curiosity, atmosphere sickness, do you guys get out sickness?
Oh, that's an interesting question.
Repeat the question.
The question was about altitude sickness, and I assume he means at Las Campanas. The good news is that Las Campanas is only about 8,500 feet or something like that. It's not very high. And in fact, you don't get sick. I have, however, observed at Mauna Kea in Hawaii, and it was probably the worst experience of my life. I'll never do it again. So in Hawaii, it's so high, it's about 14,000 feet, that usually the astronomers stay down. I don't know if you know Hawaii well, if you know the Big Island. In Waimea, it's a little town down below. And the astronomers actually work down below, and there's an operator up above who actually runs the telescope because of the altitude sickness. But occasionally, if you want to, they'll let you go up there. And I said, oh, this is an adventure. I have to observe once from Mauna Kea. And it was literally the worst 2 nights of my life. It was so painful. And my colleague who was with me was on an oxygen mask the entire time. It's just not worth it. Fortunately, Las Campanas is not so bad. Yeah.
So on a related question then, if you're in a remote building from the
Telescope.
couldn't you put that remote building in Pasadena at Carnegie?
Well, you would think. So in fact, I should point out that we do a very tiny bit of remote observing, not on the big telescopes, but the small ones from Pasadena. The problem is often the internet connection is still not terribly reliable from Chile. And there's a philosophy thing too. For me, I really love going. When I go observing, I'm in such an observing mode that I don't have to worry about what's going on at home, and worried about the dogs, and worried about this. You know what I'm saying? And everybody else, so you're very focused. And the other thing is, I like to just go out and look at the night sky. I mean, it's so incredibly beautiful. I think you saw this first image. I mean, it's unlike anything you see anywhere else. It's not up there. That is too. That's St. John's. That's pretty nice too. But the night sky, it's just nice to be able to see. And I found when I have observed from the Keck telescope down below in Waimea in Hawaii, and it's not the same because you have to ask the telescope operator, go out and is it cloudy? And he's like, well, I think it might be cloudy. I don't know, I trust my own judgment better than others. So to me, it's part of being an astronomer. What I will say is I think in the future it will become very obsolete. I think the next generation, the young astronomers, in fact, don't seem to have this tie to the sky that people like myself do. And so I have a lot of them I think are quite happy for the data just to come in. So in the future, it will be there.
Could that burst be coming from dark energy or dark matter?
At this point, it could be coming from almost anything. Yeah, I mean, so the question is, could it be related there? I think there have been some suggestions, in fact, about dark matter, whether it's some sort of an annihilation event or something. But it's only in the radio, which is strange. And so I think that I should point out that the one we saw was only the 8th one ever seen, and the only one ever seen live. And so at this point, it's such a new field. It could be almost anything, even aliens. Oh, we have a young kid. Awesome. Go ahead.
I have actually quite a few questions.
Uh-oh. It's going to be a long night.
You're good. say 3 or 4. Well, how do you actually detect the infrared and the gamma rays and these? Do you have to use special crystals or special?
Oh, that's an awesome question. Yes, the answer is yes, you need to use special techniques. And the special techniques include not only the detectors. So for instance, you can imagine your phone uses, if you take a digital picture with your phone, that technology that you use on your digital phone for taking images is very comparable to the sort of camera we use at Magellan. They're called CCD cameras. I mean, it's just a digital camera. It's very comparable. That's because you're looking at optical light in both cases. But that thing will not take a picture of X-ray emission, for instance, or infrared emission. So you have to develop special detectors to do that. But more than that, you also have to develop special telescopes. Because, for instance, X-ray telescopes, if you take an optical telescope and put it in space, it's not going to start detecting X-rays. X-rays actually would penetrate right through it. And so you need to do very special techniques to your telescopes. So, and I'm sure if there are many more questions, you can come and ask me after. I would be happy to. Oh, but the young lady next to you, go ahead.
What if there are other types of rays stronger than gamma rays that are creating those bursts?
Well, we, by definition, only know the most energetic things we know about are gamma rays. In theory, the gamma ray band could keep going. We kind of arbitrarily limit it where we see things in general. I think at this point, the burst could be almost, I shouldn't say almost anything, can be almost anything. I guess we really just don't know. So maybe it is related to something, some high energy phenomenon. Good questions. Let's see. Oh my gosh, lots of people. Let's see. Let's go back there. Another young man. Sorry. Yep.
If those black holes in the two galaxies are to mix, how would that happen?
How would they merge? Well, that's a little bit complicated. I'm not sure I could explain. I'm not sure exactly how to answer that question. Let's see. Because they're black holes are just large portions of energy, right, of mass and gravity. They're in some sense not really different than stars, and stars can actually merge as well. So what will happen is they will merge, but they merge very, very quickly. And when they merge, they may actually produce a lot of energy, gravity waves and other things. So they may be detectable. In fact, this is one of the things we're hoping to do in the future, is to try to detect black holes merging in real time. That one, unfortunately, we've caught it at a stage where it's almost merging, which is very, very interesting. But of course, we won't live to see it actually merge ourselves. That's going to take too long.
Well, all the mirrors for the giant Magellan board are cast, and you're just now polishing them up?
No. They take about 2 years to do a single mirror, 2.5 years. We are about to start the fourth mirror. So the first mirror is completely done. The second and third mirror are in the process. So the issue is the mirror lab in Arizona, where the mirrors are built, has, we'll call it stations, where they go through the various steps in the process. And there's basically one station for each step. And so, in fact, at any one time, they have many mirrors going through, including not only GMT mirrors. So unfortunately, we're kind of in a queue, basically. So the hope is, however, that we're starting the fourth mirror this year, which will be the central mirror, the one with the hole in the middle. And so the hope is that we can actually start the telescope with the 4 mirrors, 3 outer mirrors and the inner mirror. So that'll be kind of an early version of the telescope. And that's very, very exciting, because it means we'll be able to get on sky very early. And it will be by far the biggest telescope in the world, probably many years before any other telescopes. Yeah, sure.
How do those giant mirrors get from Arizona?
Their journey's worse than my journey, to Les Campanas. What happens is they actually get put on a truck from Tucson, and they drive them to Long Beach. And they will shut down the freeway, probably come right through town here, shut down the freeway at 3 in the morning sometime, and send them out to Long Beach. They get on a ship, and then they go down to Chile, and that takes 2 to 3 weeks, I think, for them to get down. And then they get in La Serena, the little town I showed, which is about 100 miles or so from the mountain. They'll get off the port there, and then they go up the mountain very, very carefully. Now the question, the mirrors are worth about $20 million each, so you want to be careful. And it takes 2 years to build one. So I should point out we are doing an 8th mirror, but not for that reason. We're doing the 8th mirror because you always want to be cleaning one of the mirrors. And so we'll have this process where there'll be 7 in the telescope and 1 will come out, and then we'll put the spare in. But there will be 1 spare, but certainly we can't afford to have them break. But it's a big concern. And so the real question, I think, is for Magellan, 1 mirror came up, and then the next mirror for the second telescope came up like 3 years later or something. There was a gap between them. you have 7 of these or 8 of these. Do you do them all at once? Do you close down LA for, I don't know, hours to carry these mirrors through to Long Beach? I don't know. We haven't got that far. I think first we have to make the mirrors.
Can you speak about sea bass? Do you know anything about the sky survey?
I don't know anything about sea bass that I could say with authority, I'm afraid.
Yes, you were talking about, by the way, thank you for it was a phenomenal lecture. I loved it. Thank you.
Oh, good. I appreciate it.
You talked about it appeared that the dark matter was not interacting itself. What would be the most promising theory or like?
Oh, gosh. I wasn't going to show that slide because I was worried somebody was going to ask me that. I don't know the answer. I should say that the dark matter is almost certainly at this point to be some subatomic particle. I think we're pretty clear on that. We've eliminated all, for a while, could it be planets? Could it be black holes? There were all these various experiments the astronomers have done that have actually eliminated pretty much anything astronomical. And at this point, the only thing really left is some subatomic particle. So it's one of these really interesting things I like to tell people. Physicists now think astronomy is really interesting because we've uncovered the 2 biggest problems in physics, which is dark energy and dark matter. And these were uncovered by astronomers from observations, but I think, personally, it's up to the physicists to now explain it, because in both cases, it's some sort of phenomenon related to physics. So quite likely, there are dark matter experiments that are being done by physicists trying to detect things, but quite likely, it's going to have to come from some new understanding of particle physics, I think. I don't think there's anything I can do as an astronomer except, we get the scale of the dark matter and the amount of dark matter, all those sorts of things is what the astronomers do. It's really up to the physicists at this point.
What is the approximate latitude of your observatories, 34 degrees?
It's minus 29. Minus 29, yeah.
The reason?
What's that?
The reason?
The reason is really because it's at the very bottom of the Atacama Desert. We're not in the driest part, where it's really almost impossible to live. And it's kind of the closest one could get and have really a dark sky. So the thing is, the key is that it's far from anything else. The little town I showed you, Las Serenas, like I said, about 100 miles away, that's the only really nearby town. The good news is because it's a desert, it's unlikely to be developed. We learned our lesson at Carnegie. Carnegie, of course, built the Mount Wilson observatories up here, which were at one time the finest observatory in the world. But as you can imagine, Los Angeles grew up and that's no longer the case, right? And so the key with Chile, this is a very remote location that's very dry and I think unlikely to actually ever have any real light pollution from development. Sorry?
Same condition you find in Australia as well as South Africa?
So there have been telescopes in both places, but Chile tends to have the better what we call scene, which is image quality. Chile, I like to tell people, you might even be able to see from the pictures there, Chile and California are so similar. So, if you take a picture from one, I bet a lot of you couldn't tell where it was. And it's the same sort of climate that we have here, except Chile's just a little bit drier. And it turns out that the stability of the air is just really wonderful in Chile. So the image quality, there's no question in my mind that the image quality is much better in Chile than anywhere else, including Australia and South Africa. That is not to say, however, that telescopes are not being built in those places. The Australians and South Africans certainly are building telescopes in their home countries because it's a lot easier than flying to Chile. But for us, it really is the best choice. Let me take one more question, and then if there are other questions, you can come and see me. Hi.
What percentage of the entire universe is made out of the dark matter?
That's a good question. So the universe is about 4% of the universe is made of the stuff we know about. This is the stars, the planets, the dust, and gas. Then about 27 or 28% of the universe is made up of dark matter. So in fact, dark matter actually dominates the matter portion of the universe. The rest is what is known as dark energy, which I know even less about dark energy than dark matter. So, but you're going to hear from the world's expert on May 11th, so that's a good excuse to come back and see Bob Kirshner. But so basically, did that answer your question? So basically the answer is dark matter makes up about a quarter of the universe. So, and we actually know that from several different ways now. Experiments like the one I showed you for NGC 2276, we've done that calculation for a long time now, and that's one way, but there are other ways we've actually reached the same conclusion. Okay, I think at that point, I'm the host and the speaker, so let me, okay. And if there are further questions, I'm happy to answer some. Thank you. We hope to see you in 2 weeks.